So the first thing is, how do we know that something like sodium hydroxide dissolves and sodium chloride dissolves? Can you think of some salts that don't dissolve? So for example, rust. You know, rust can be thought of as a salt. It's iron 3 oxide is rust. Can you just wash off the rust off things? Will it wash off? Does it dissolve in water? No, rust doesn't dissolve. How about your copper pennies? They get oxidized, so they form a kind of a salt on the surface. Is that? Can you wash off your pennies and clean them that way? No. And so some salts are soluble, some aren't. And so the green ones here are soluble, the red ones aren't. And then there's some that are in between. And so what we need to do is we need to memorize these. But do you want to memorize this chart here? No, probably not. Because this chart is 2 pages long. And yeah, we don't want to memorize it. And so what we're going to do is we're going to not memorize this chart. We're going to memorize a simplified, or more simplified. In fact, this has already been simplified because if I wanted the specific details about solubility, do you know a book I'd consult if I wanted to know if something dissolves and how much it dissolves? The CRC handbook. I'd look there. And so this is already taken from that. It's been simplified. We're going to simplify it even further. And so when I look at it, I go over here, I see simplified solubility rule. Right? That's reactions 1. And so I'm going to look for reactions 1 up here. Looks like I passed it. Here's reactions 1. And these are the simplified solubility rules. But, you know, I don't like this format. So I'm going to skip this one. And I'm going to go to Chem Compact G. In Chem Compact G, page 127, I like this, the way it's formatted here. It's a little bit easier for me to read. And so you're going to have to memorize these, but there's one thing I need to change on that. One thing I'd like to change is this. When you look at all these, what do all these have in common? They're all anions. And so before we look at the anions, the first step is to look at the cation. So step 1, check the cation first. If the cation is group 1, or ammonium, just say group 1 and ammonium, then these are soluble. This is like sodium chloride. Sodium is group 1, soluble. Sodium hydroxide, sodium phosphate, sodium chromate, sodium carbonate, sodium bicarbonate, sodium whatever is going to be soluble. So that's why we're going to look at that first. That goes for any group 1. Group 1, the alkali metals, the first column of the periodic table. Okay, then we're going to look at the anion next. Then we have 2 subcategories. The ones that are mostly soluble. The mostly soluble ones, we'd start off with that. C2H3O2 minus. These are called this anion is called acetates. Acetates, chlorates, and nitrates. These are soluble. And so it doesn't matter the cation here. Iron 3 nitrate. Soluble or insoluble? Soluble. Lead 2 acetate. Soluble. Doesn't matter the cation. Okay, what's the next series of anions? We're going to look at the chlorides, bromides, and iodides. Chlorides, bromides, and iodides are soluble, except there's some important exceptions here. There are exceptions here too. You know, not every single group 1, most of them. So there are rare exceptions in some of these, like sodium uranyl acetate. Soluble or insoluble? Sodium uranyl acetate. Well, it's a sodium salt, so you'd say soluble, because all sodium salts are soluble. Well, I would have gotten you there because sodium uranyl acetate is insoluble, meaning it doesn't dissolve. But how often do you work with sodium uranyl acetate? Never. It's okay. And so they're going to, you know, these are rules. Are these laws? No, these are rules. So this is chlorides, bromides, and iodides are soluble, except these are important exceptions. Silver. So if I look at silver ion, I could have silver chloride, which is insoluble, silver bromide, insoluble, silver iodide is insoluble. And so what does it mean to be insoluble? It means that, you know, the lattice is too strong to break apart. You know, the water molecules are going to come in there and they're going to try to tear apart the lattice. Are they going to be successful with silver chloride, silver bromide, or silver iodide? No. And so the water molecules are going to try and try, but they aren't going to be fully successful. Lead 2 chloride, lead 2 bromide, lead 2 iodide, insoluble. Mercury, what's this one called? Mercury 1 or Mercury 2? Mercury 1. Mercury 1 chloride, Mercury 1 bromide, Mercury 1 iodide, insoluble. Those lattices are too strong. 3 would be sulfates. Sulfates are going to be soluble, except silver, lead 2, mercury 1. But now we have some more. In addition to mercury 1, we have mercury 2, calcium, strontium, and barium. And so we say sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. You can make a little song for it to help you memorize or something, you know. So that's it. A lot more exceptions, but still, it's doable. Most people. Okay, if it's not a mostly soluble anion, then it must be a mostly insoluble. So let's look at the ones that are mostly insoluble. These ones won't dissolve. The first one we look at on the mostly insoluble end of things is this one, hydroxide, OH minus. Hydroxides are insoluble. Insoluble. Except, well, this one we've already looked at. Group 1 and ammonium. You know, we checked that one first, so we don't really have to check it again. But all group 1 and ammonium salts are soluble. And then calcium, strontium, and barium. And so hydroxide are insoluble except group 1, ammonium, calcium, strontium, barium. 2, sulfides. Sulfides are insoluble except this one, group 1, ammonium, and group 2. group 2, magnesium. You know, magnesium, calcium, strontium, barium. Those are group 2. Those are soluble. And then finally, we have this. We have phosphates. Phosphates are, oh, no, not just phosphates. What else do we got? We got carbonates, chromates, and phosphates. Carbonates, chromates, and phosphates are insoluble, except for group 1 and ammonium. That's it. And so work on memorizing these. There. So as you memorize these, you know, you'll hit a point where you got to memorize. And then as you review them, you know, it becomes easier and easier, and it becomes kind of boring a little bit. You know, you've seen it so many times, it becomes boring. Well, when you've seen it so many times, it becomes boring. You start to look for different things. And when you start to look for different things, you start to look for patterns. Do you see any patterns in this? Somebody who crams these overnight will probably not see any patterns. But somebody who's been going over these a whole bunch of times may see some patterns there, because you know it takes time to see patterns. Sometimes the patterns are obvious, sometimes they're not so obvious. The reason I ask this is because, you know, there are different things you can do. You know, a lot of people will say, okay, I memorized these. Okay, good. You're supposed to memorize these. But then they'll say, well, you know, you gave a question on the test, and that question wasn't fair. The question wasn't on this list of things to memorize. And it wasn't in the homework, and it wasn't in the book. So why are you giving a question that's not in the homework, not in the book, and it wasn't one of these that you asked us to memorize? And I said, well, you know, because, you know, to understand things a little bit more deeply, this would be the next level. The next level is maybe you could see a pattern there. Because if you could see a pattern there, do you know what's missing on this list? You know, oxides are missing on this list. There are other things that are missing off this list. Well, you know, maybe you could guess, you know, maybe it should be more soluble or less soluble depending on where it fits in the pattern. And so do you see any pattern in the solubility rules? So one thing, you know, somebody who just looks at this initially will say, hey, you know, they might not even notice this, but after a while you might notice this. Hey, where's fluoride? Isn't it fluorides, chlorides, bromides, iodides? Where's fluoride? Was that just a typo? Or was that intentionally left off? Was fluoride a typo or intentionally left off? It was intentionally left off. Why was it intentionally left off? What do you think? Because there are a lot more exceptions. There are a lot more exceptions with fluoride. And so if we included fluoride in here, all of a sudden it gets a lot messier. And so the best thing is, if you have a fluoride, the best thing to do is to look in the CRC handbook. You know, if you care about fluoride, look in the CRC handbook because it's more complicated. We can't simplify it so much. There's another thing that's missing too. That's pretty obvious. It's missing. Here, What happened to beryllium and magnesium? Why is it only calcium, strontium, barium? Shouldn't at least magnesium be included there? Like magnesium, calcium, strontium, barium? Well, maybe magnesium's not important. Is magnesium not that important? So we can just ignore it? What do you think? I can understand leaving off beryllium. Did I tell you about my friend who worked at, I think he's still there, works at JPL? Did I tell you about him? He was working with ultra high vacuum stuff, and he had a whole bunch of these steel cylinders. Some of them had windows in them. And some of the windows were made out of beryllium. And so he asked, because he bought these as surplus items, so he asked me if he could store these in my garage. And I didn't, after I found out they had beryllium windows, I'd rather not. Why? Because beryllium is super toxic. Beryllium they used to machine for aerospace, and then all the machinists who machined beryllium ended up dying, all of them. They figured out it's because of beryllium. Beryllium is very toxic. And so instead they use magnesium, and they use, calcium's too soft, they just use magnesium and titanium. But beryllium is ultralight metal. But anyway, why is magnesium left out? Is magnesium not important? Beryllium for sure is rare, because nobody wants to touch beryllium, nobody wants to use beryllium. It's so toxic. Is magnesium rare? No, magnesium's common. And so, was it accidentally left off, or was it intentionally left off? It was intentionally. Why do you think they intentionally left it off? Too many exceptions. Too many exceptions meaning there are a lot more that are insoluble, or there are a lot more that are soluble? Insoluble, right. The other, patterns take time to develop. And it's not just scientists it takes time to develop, but also the social scientists. It takes time to develop. I was watching this TED Talk, and it was like one of the top 10 TED Talks or something. And it was this social scientist, and she was talking about how she does research, and she said something to the fact that she throws all the data on her floor, all the papers are strewn out over her floor, and then she gets in the chair and just stares at them essentially, so just staring at the data. That's what you got to do, because if you just look at this one time, there's no way you'll be able to see the pattern. You got to look at it repeatedly. It's like the ABCs. If you just do the ABCs once, then maybe you'll forget it. Let's say your native language is something else. It's that repetition. Remember, well, it's the same thing with the solubility rules. You're going to have the people who don't memorize it. Well, that can't be helped. Some people, they just refuse to memorize it. Then you'll have the people that just memorize it, but that's all they can do. They've just got to memorize. And so the only questions they can answer are the questions given as is. And then you have the people who've looked at it so many times that it's kind of boring, and they look for new things. They look for patterns, they look for questions, they start asking questions about the data. And those are the people who might be able to answer things beyond this chart. Because, it's two different levels. If you see a pattern here, that's good, because then you might be able to apply the pattern to things that don't apply to the chart, right? And that means that you can actually answer questions that aren't exactly the same as the homework, and aren't exactly the same as what was presented in lecture, or exactly the same as written in the book. You can answer deeper questions based on the pattern. And so let me ask you this. What do the things that are insoluble seem to have in common? What types of things make things less soluble? Metals? Well, There are some exceptions. Ignore silver for right now, but look at some of the other stuff. We'll ignore silver. Like for example, group 1 and ammonium. Group 1 and ammonium are soluble. Yeah, but what about like group 2? Or what about group 3? And what's the difference between group 1 and ammonium and the other metal cations? Well, group 1 and ammonium, what do they all have in common? They're all +1. But what about calcium? What about aluminum? They have a higher positive charge. And so it looks like the lower the charge, the more soluble. The higher the charge. Okay, now look at what about phosphate? Is that high charge or low charge? Well, not just, we've got to look at the imbalance here. The imbalance would be the charge on phosphate is 3 minus. What about the charge on chlorides, bromides, and iodides? And chlorides, bromides, and iodides are mostly, carbonates, chromates, and phosphates are mostly insoluble. Do you see a pattern? I see a pattern, and the pattern to me is this. When we're looking at a lattice, ionic lattice, what holds the lattice together? What holds the lattice together is attraction between positive and negative. It's an ionic lattice. That's what holds it together. And what do we call that force of attraction between positive and negative? What's that called? Electrostatic forces. Do you guys recall electrostatic forces, seeing that? This should be like, chapter 1 and chapter 2 should be like going back to kindergarten, right? Hopefully by this time it should be like going back to kindergarten. So if we go back to chapter 2, which should be like maybe first grade. Maybe chapter 1's like kindergarten, chapter 2's like first grade. Then this should be pretty straightforward for you. And that is, what is that? Well, that is this. Do you guys remember this? The pith balls? This is why charge is so important. I mean, you don't even pay attention to charge. Opposite charges, like charges, repel. And so this is huge. It's huge. In fact, we want to look at this charge in much more detail. And so is there a law that describes this force of attraction? Coulomb's law. Did I talk about Coulomb's law already? What does Coulomb's law depend on? Yeah, good. Wow, that's much better than this morning. Nobody remembered Coulomb's law this morning. That's good. Coulomb's law depends on the charge on body A and the charge on body B divided by the distance. Well, let's look at the charge. If I change the charge from +1 to +3, what just happened to the force? If I change the charge from +1 to +3, then the force just tripled, right? So if ZA goes from 1 to 3, the force is tripled, meaning that the lattice is going to be much stronger. Likewise, if I go from -1 to -2, it just doubled, right? And so we can see, hey, this is not on the list, but what do you expect this one to be? Soluble or insoluble? Just take a guess. Soluble or insoluble? Is it a flip of the coin, or can you give it an educated guess? Insoluble. And you might go, hey, that's not fair. That wasn't on our list to memorize. That's not in the book. You're right. It's not in the book. It's not on the list. But it's fair. It's fair because somebody's going to be able to answer it. Maybe not you, but somebody in the class will probably be able to answer it. Hopefully you will be able to answer it, right? Because this stuff, this is the reason why aluminum used to be a very valuable metal. Because, what do you use aluminum for? Are you going to build an airplane out of steel? Would you build an airplane out of steel? Lead? Would you build an airplane out of lead?
Copper? No. Why? Because those are way too much. You're going to build it out of a lightweight metal like beryllium. Well, don't build it out of beryllium, because all the machinists who were machining beryllium during the war years ended up dying. Not instantly, but over time, due to beryllium poisoning. You're going to machine it out of magnesium, you're going to machine it out of aluminum. Magnesium, where do they get that? Get it out of the oceans. You get the magnesium ion converted into magnesium metal. Where do they get the aluminum from? Do they get the aluminum out of the oceans? No, they mine it. And they mine it from this. You know what this is called? What's the ore called? David, you guys know this. Or no? Bauxite. You know, there are islands in the Caribbean that are made almost entirely of bauxite. But the problem with bauxite is it doesn't dissolve in water. It doesn't dissolve in water because they got to separate the aluminum ions from the oxide ions so that they can convert the aluminum ions into aluminum metal. And so it used to be very expensive because the only way to separate this is to melt it. But do you know what the melting temperature of bauxite is? Or this is also called alumina. Or alumina is a ceramic that people use. It's also called a carborundum. And it's very hard. You know what the hardness of this stuff is on the Mohs hardness scale? This is like 9. Diamond is 10. So this is almost like diamond. I mean, so to melt this, it melts at an extremely high temperature because why? Because the ions are held together so tightly because of these very strong electrostatic forces. Right? This lattice is very strong. Very strong. Extremely hard to melt and doesn't dissolve. Very strong lattice. It turns out that the person who figured out how to get this stuff to dissolve became one of the richest people in the world. Do you know this story? Yeah. Huh?
You mentioned it, but like you can't think of the date.
All right. Yeah. And then because what they did was they made aluminum from a precious metal into aluminum as a common metal and a cheap metal, and in the process became very, very wealthy. This happened in the 1800s. But anyway, in order to figure out how to get this to dissolve, we have to understand, some basics. Do you think the person who figured out how to get it to dissolve just tried lots of different liquids, one after the other, and they just got lucky on the trillionth liquid they tried? Oh, it dissolved. No, they had some kind of strategy. They were looking at some kind of pattern. It's not just random. And so the same thing here. Okay, what else does it depend on? Coulomb's law depends on the charge of the cation and the anion and d squared. D squared is the distance between charge centers. And so let's look at fluoride. Let's look at something like magnesium fluoride versus magnesium chloride. Well, it turns out that chloride is much bigger than fluoride. And if I look at the distance between the center of the charges, that's looking at the distance between the center of the ions. And the further the distance is, the weaker. The shorter the distance is, the stronger. And so if we're looking at fluoride versus chloride, of course fluoride is going to have a stronger electrostatic attraction because it's smaller. Of course, beryllium. This is why beryllium is so toxic. Do you need magnesium to live? Can you live without magnesium in your body? No. But if beryllium were present, do you know what beryllium would do? Beryllium has a much stronger electrostatic attraction. Therefore, beryllium is going to force magnesium out and beryllium in. And so if you have proteins or whatever that rely on magnesium, well, forget it, because the beryllium is going to come in there and dominate. Why? Well, here's where small size matters, because it's smaller. Right? Usually you think, oh, it's bigger, it's going to dominate. No, in this case, it's smaller. It's going to dominate. Okay, so electrical forces are important, and therefore the charges make all the difference in the world. And therefore that's why we spend so much time looking at the charges and memorizing the charges and doing this or doing that. You know, so now I didn't use all my drain cleaner. I still have some sodium hydroxide left. You know, I have sodium hydroxide. Is sodium hydroxide soluble in water?
Yes.
Yeah, but do you know I have something else at home? I have this stuff. This is, both of these you can buy in the supermarket. This one is called Lye. And I know they have this at Ralph's, because when I was there, but Ralph's is much more expensive. You're going to buy it there, so that's why I went to Orchard. It's a lot cheaper. Or any other place. You know. They have this too. And I had some, but I ran out because I don't like drinking this stuff at all. I don't like drinking this stuff. I had something else that was similar to this. But anyway, do you know what this other stuff is here? What's the name of that? Magnesium hydroxide. You know, I drink this stuff because this is called, although I haven't had it in years, milk magnesia. Milk magnesia. It's like a paste. You know what's such a paste? It's a paste. It's like you're eating chalkboard paste. It's awful. But let's say, you know what? When my drain clogged, I didn't look for the milk magnesia because I was thinking, my drain clogged, I need some sodium hydroxide. But I have some magnesium hydroxide in the medicine cabinet. Should I just grab the magnesium hydroxide and start dumping milk magnesia down the sink? It's not very effective. You know why? Because magnesium, what do you know about magnesium hydroxide versus sodium hydroxide? The forces are weaker in what? Opposite. The forces are stronger, right? What's the charge on sodium? What's the charge on magnesium? So twice as strong, ignoring the size. Then we factor in the size. So hydroxides, none are soluble except calcium, strontium, and barium. So calcium hydroxide is soluble, but magnesium hydroxide is soluble or insoluble? Insoluble. So this is why it was a paste. It was a paste because I was eating little crystals of magnesium hydroxide. Right? They weren't soluble. And so if I did this, I'd get a paste clogging my sink drain. You know, do you want a paste, a white paste? Actually, it's a pink paste, but do you want a pink paste clogging your sink? No. Whereas the sodium hydroxide, that is soluble. So when you dump that in the sink, it'll start to attack the fat, right? Magnesium hydroxide just kind of sits there. Let's say, you know what, they use magnesium. This is an antacid, by the way. So let's say just the opposite happened. Let's say I ran out of antacid, and so there's no milk magnesia to drink. But I do have some drain cleaner. Should I drink the drain cleaner instead? Would you recommend, hey, it's magnesium hydroxide, sodium hydroxide, what's the difference? Same thing, right? Would you drink the drain cleaner to help your acid reflux or stomach acid or whatever? Yeah? Why not? It's a hydroxide, both are hydroxides, why not? Why not? Because sodium hydroxide will kill you. Because it's
sodium hydroxide is soluble, and so it makes a world of difference here. Magnesium hydroxide is in. You know, I had a CAT scan, and I had to drink barium cocktail. The barium cocktail was barium sulfate. Is barium sulfate soluble or insoluble? Insoluble, so it was like milk and magnesia. It was a paste. I drank the stuff. It's pasty. It's insoluble. Even in stomach acid, it really doesn't dissolve, even in stomach acid. Which is a good thing, because barium is highly toxic. You know, if they gave me a barium chloride cocktail instead, I would be very sick, because barium chloride is extremely toxic, whereas barium sulfate is generally regarded as safe enough. You know, that was for the first CAT scan. The second CAT scan I had, I was given iodine instead. I had an allergic reaction, so I'll probably, if I ever have another one, I'd probably have to go back to barium sulfate instead. And so it was cherry flavored. Milk magnesia, I think, is like strawberry flavored. Both are awful. I prefer other antacids. But you know, this is a world of difference. Why? It's the barium. Barium. This is like you know, the windows. You know why they use beryllium windows? They use beryllium windows because they're ultra lightweight. They have very few electrons, so X-rays easily pass through beryllium windows. They don't have very many electrons, so the X-rays interact with electrons. If I use lead windows, would lead windows work well for X-rays? No, lead windows would completely block out X-rays because lead has a lot of electrons. Well, CAT scans are using X-rays, and so barium has a lot of. Barium's near the bottom of the periodic table. Barium has how many electrons? 56 electrons. Of course, they could have given me a lead cocktail, but I would have refused the lead cocktail. Lead would work even better because they would image lead much better because it has more electrons. Lead has how many electrons? 82 electrons. And so lead works very good, absorbing X-rays. Well, barium works pretty good too. So that's what barium. Iodine's pretty good too. Iodine has a lot of electrons. How many electrons does iodine have? 53 electrons. All right, so so of course we want to understand things a little deeper so that we can go beyond, you know, straight memorization. And you know, a lot of people will go, well, what's the use of memorizing solubility rules? It's not just memorizing. If we're just memorizing, then there's no use to it because, you know. But what we're doing is we're trying to memorize and seeing, is there some kind of pattern to this, you know? That way we can extend the knowledge beyond just memorizing. And so there's a huge movement against memorization. You know, all these studies that prove that memorization is worthless. But, you know, I totally disagree with that. Totally disagree. You got to have that basic stuff memorized so that you can see the patterns. How are you going to see these patterns without memorizing this stuff, right? So, you know, so if you get lead, you know, if they give me a lead cocktail, then I'm going to get, you know, high lead levels in my blood. That's not good, right? And so if they gave me a lead cocktail, you're going to have to give me some kind of medicine to get rid of that lead. Do you know what medicines are available to get rid of lead in your blood? Are there any medicines? There are. There are two medicines available for getting rid of lead in your blood. One is called sodium EDTA. The other is called calcium EDTA. These are two medicines that were available for getting rid of lead in your blood because these medicines will attack the lead, actually encapsulate it so that you can excrete the lead safely. Right? We don't want the lead because what happens with lead is it reacts with sulfur in proteins and screws up the proteins basically, and other problems I think as well. Which of these two drugs do you think, you know, one of these drugs is aggressive, the other is non-aggressive? Or not, I shouldn't say non-aggressive, less aggressive. And so which of these is more aggressive? Which one is less aggressive?
You say this one's more aggressive? This one is less aggressive? It's like drain cleaner, you know? Which drain cleaner is more aggressive, which drain cleaner is less aggressive? Sodium hydroxide or magnesium hydroxide? You say sodium hydroxide, you would say magnesium hydroxide, is that right? Because what's happening, is it the sodium that's attacking the fats, or is it the hydroxide that's attacking the fat in the drain? It's the hydroxide. The hydroxide is attacking the fats in the drain. That's why you can make soap. When people make soap, they can use sodium hydroxide, they can use potassium hydroxide, they can use lithium hydroxide to make soap. They use potassium hydroxide to make mostly potash. But it's the hydroxide that's attacking. What do you think? Is it sodium ions or calcium ions that are removing the lead out of your blood? Or is it the EDTA that's removing the lead out of the blood? It's the EDTA. So if I asked you which one's a better drain cleaner, sodium hydroxide, which is called Red Devil Lye at Ralph's, I looked at recently, or milk of magnesia, which one's a better drain cleaner? Why? Because I told you, or why? Why? Well, if we look at this, this is solid, right? And the active ingredient here is the hydroxide. So what happens here is I dissolve this in. This one dissolves in water, and what does the water do? Breaks apart the lattice, and I get sodium ions and I get hydroxide. The hydroxide ions go on to attack the fats in the drain and clear the drain. They'll attack the fats and make soap. Well, the soap happens to be water soluble, and I can do it, so I just dumped in. I dumped in a huge amount. And it did clear the drain. It worked pretty well. Whereas magnesium hydroxide, what can we say about magnesium hydroxide? Is it very soluble? No, it's insoluble. If it's insoluble, are you going to have the hydroxides free to attack the fat, or the hydroxide's going to be locked in a lattice? Locked in a lattice. So which one's going to be a more effective drain cleaner? Sodium hydroxide. Which one do you think is going to be a more aggressive drug? Sodium EDTA or calcium EDTA? Sodium EDTA. It's a simple electrostatic principle. Simple electrostatic principles. This is the CDC report here. The CDC report on this is called chelation therapy, intravenous IV chelation therapy using calcium EDTA, sodium EDTA. Calcium is a 2+, sodium is a 1+, so that's why it's Na2 EDTA. EDTA, we can write out the formula for it, but it's kind of long. Therefore, they just use the abbreviation. One of these, they use both because this one's more chronic, this one's more acute, and high level. And so, sodium EDTA contains a warning stating the use of this drug is recommended only when the severity of the clinical condition justifies the aggressive measures associated with this one. And so the sodium EDTA is aggressive, the calcium EDTA is not as aggressive, correct? And so if you have pediatric patients, which one do you think you're going to use on children? The sodium EDTA or the calcium EDTA? calcium EDTA. So this always kills me. I've read this so many times, but it's hard to read. This is Texas, February 2005. A girl aged 2 years who was tested for blood lead during routine health surveillance had a capillary BLL, blood lead level of 47 micrograms per deciliter. A microgram per deciliter, that is a part per million, we can figure it out. A venous BLL of 48 micrograms per deciliter obtained 12 days later confirmed an elevated BLL. A complete blood count and iron study conducted concurrently revealed low serum iron levels and borderline anemia. On February 28, 2005, the girl was admitted to a local medical center for combined oral and IV chelation therapy. The patient's blood electrolytes admission were within normal limits. Initial medication orders included intravenous sodium EDTA, oral Sexamar, an agent primarily used for treatment of lead poisoning. The medication order subsequently was corrected by the pediatric resident to intravenous calcium EDTA. At 4 p.m. on the day of admission, the patient received her first dose of intravenous calcium EDTA, 300 milligrams and 100 milliliters normal saline at 25 milliliters per hour. At 4:35 p.m., she was administered 200 milligrams of oral Sexamar. Her vital signs remained normal throughout the night. At 4 a.m. the next day, a dose of intravenous sodium EDTA instead of intravenous calcium EDTA was administered. An hour later, the patient's serum calcium decreased to 5.2 milligrams per deciliter. Normal value for pediatric patients, 8.5 to 10.5 milligrams per deciliter. At 7:05 a.m., the child's mother noticed that the child was limp and not breathing. Bedside procedures did not restore normal cardiac rhythm, and the cardiac resuscitation code was called at 7:25 a.m. The child had no palpable pulse or audible heartbeat. Repeat laboratory values for serum drawn at 7:55 a.m. indicated that the serum calcium level was less than 5 milligrams per deciliter. Despite repeated doses of calcium chloride, all attempts at resuscitation failed, and the girl was pronounced dead at 8:12 a.m. So, you know, you think, okay, but that's not, Pennsylvania, 5-year-old boy dead. Oregon, 53-year-old woman dead, et cetera, all from accidentally giving sodium EDTA instead of. And so that's like giving if somebody has an upset stomach, you give them drain cleaner. That's what these people are doing. They're giving drain cleaner for an upset stomach. Kind of. And so anyway, the CDC, after so many deaths, finally recommended what? To get rid of sodium EDTA. So sodium EDTA is no longer on the shelf, so you can't make this mistake. But how many people had to die? Ridiculous. So for me, it's like, okay, yeah, it seems kind of ridiculous, drain cleaner versus milk and magnesia, but this is not. Nobody would mistake drain cleaner with milk and magnesia, so maybe they should write that on there, drain cleaner. Don't use that. But anyway, that's it for today.